Now let's continue our discussion of superpositions by looking at the general one-dimensional box wave functions. In the last video on superpositions, we talked about a general example of a sine function. In this video, we're going to be looking at the one-dimensional box functions, solutions to the Schrodinger equation, which you will recognize as actually being very similar to the last example. So you can probably already figure out what the results would be, but we're going to go ahead and do this anyway. Now again, let's talk about momentum. In the case of momentum, we know that in order to figure out what the outcomes would be, we're going to have to figure out a superposition of eigenfunctions of the momentum operator, because our sine function is not an eigenfunction. So there's more than one possible outcome, as we indicated in our last discussion of superposition. So we're going to run through the same thing. Here we go through the process of writing it as exponential functions, which we see right here. So I've converted our sine function using the trig to exponent function into this linear combination. And just again, that means we get these two possibilities here in our term. All right. If we then operate on that function, the linear combination, in each of those terms with the momentum operator, we get this. Okay, so this is still kind of confusing. First of all, is it an eigenfunction? Well, yeah, if we take a look, we can see that embedded in our function here, in our result, is in fact the eigenfunction for the momentum operator. So we do have an eigenfunction, but amongst all these constants here, what are the eigenvalues? Well, the best way to figure that out when we have an eigenfunction situation is just simply take our result and divide it through by the function itself. So here is our function. Okay. If we divide through our result by our function, we're going to get our two terms, m pi h bar over a, plus or minus, as being the result. And again, we probably could have guessed that based on our previous discussion, but this just goes through and shows another example. So that we have two momentum eigenvalues, plus or minus m pi h bar over a. And as you could probably determine based on our previous discussion about the coefficients are identical in magnitude. So therefore, the probability of measuring each of these is 50%. So just to summarize here, in the case of our momentum measurements, we're going to have two possible outcomes because we have a linear combination of two terms. Here are the two outcomes, negative n pi h bar over a and positive n pi h bar over a. And each of them having the same coefficient has an equal probability. So there's a 50% probability of measuring either one. Now let's look at an interesting case where we are actually going to have a wave function that is a superposition of energy eigenfunctions, which in fact are the particle in a box wave functions. So here's an example where we've got these wave functions that are particle in a box wave functions, psi 1, psi 2, psi 3, corresponding to n equal 1, n equal 2, n equal 3. And we have this linear combination with the coefficients of 0.5, 0.5, and the square root of 0.5, respectively. So that's an interesting situation. Our wave function is a linear combination of these functions. Now, since these wave functions are eigenfunctions of the particle in a box, for the particle in a box of the Hamiltonian operator, these were the solutions to the Schrodinger equation. So therefore, they are eigenfunctions of the Hamiltonian operator. Each one of these corresponds to a different energy measurement. Right? Let me repeat that. These are eigenfunctions of the Hamiltonian operator. Each one corresponds to a different energy measurement. So that means that this wave function representing the state of our system has three possible energy values that we can measure. The energy is uncertain. And that certainly seems weird, right? How can that be? How can we have a state of the system where the energy is uncertain? Well, the answer is we can. Quantum mechanics allows us to do this. It's very interesting and very unusual in how we perceive it. So that's what we've got. Those three possible outcomes, just to write them in here, would correspond to n equal 1. So when n equal 1, remember that the wave function is n squared h squared over 8m a squared. All right, and so that means that we've got these three different values here. So the energies that we get, we'll use the table function to generate this for these three values, are going to be so we're going to generate it for n equals 1 to 3, are given here. So we've got, and this has gone through the simplification process, but we got h squared over 8ma squared. We have 4 squared over 8ma squared, which reduces to 4 over 8 reduces to 1 over 2, and 9h squared over 8ma squared. So these are the three different energy values we would get if we went through the process and measured it. Okay? Now, is our function normalized? Is this a normalized wave function? Well, all right, just taking a look at it, we see that we know that each of our wave functions here, because they're particle in a box wave functions that we entered above, each of those is normalized. But is our entire function normalized? Well, we'll just integrate. From 0 to 1, we'll just do that. We'll set a arbitrarily equal to 1. And we indeed find that the value is equal to 1. So we do have a normalized function. Great. We can also show that more generally if we just leave it as a and not define as 1, we can still show that the function is normalized because the integration over all space, that is the region of the box, is still equal to 1. Okay. All right, we can graph these functions, this function, again with an arbitrary length of the box equal to 1, and we see this is what it looks like. And you may notice that unlike the regular particle in the box functions, which we had discussed earlier, which are symmetrical within the box, this one is very definitely not symmetrical. There is a maximum probability of finding it somewhere in the first half of the box, which, as we learned earlier, we can determine by taking our probability density and using any of several functions that is available through Mathematica. But if we do the find maximum function using the probability density squared, the probability density, which is our wave function squared, we find that the maximum's at roughly 0.2. All right, so this is what we're saying here, is we've got a situation where we can see that we have a normalized function, which is a linear combination of 3 energy eigenfunctions, meaning there are 3 possible energy outcomes, and we have a probability distribution given by this, which shows a maximum at x equal to 0.20. We can also determine the expectation value, the average value for a position measurement, by remembering our simple formula for the expectation value, which is psi star and that should be psi 3, not psi e, times x, which is our position operator, times psi, which again is psi 3x1. And of course I've written it out as we did earlier in our discussion, but just to make it clear, in this case, because our operator is just multiplication by x, this is just x times their wave function squared. And we're going to integrate between 0 and 1. and we find the average is 0.27. So again, unlike our particle in a box wave functions, which were solutions to the Schrodinger equation and therefore eigenfunctions of the Hamiltonian with a very specific energy as the outcome for their measurement, in all of those circumstances we found that the midpoint was 1/2. In this case, the average value was not 1/2 but 0.27. So again, we're seeing this kind of lopsided asymmetrical function, which is very clearly maximized at roughly 0.2. Very, very different from the solutions to the particle in a box, which were just eigenfunctions themselves. Now, we can also go through the process and ask, okay, what about this question? Is it an eigenfunction of the total energy operator? We should already know the answer to that question, because if each of our functions in the superposition is an eigenfunction of the energy operator, and they each have different eigenvalues, that means there are 3 different energy values that we can measure, and that means it cannot be an eigenvalue, an eigenfunction of the Hamiltonian value operator, because there's more than one. Okay, we see here then if we take our Hamiltonian operator, which is negative h bar squared over 2m, times the second derivative, operate on our wave function, we get this beast right here, which is very definitely not an eigenfunction of the Hamiltonian operator. Again, that has to be the case because there are 3 possible outcomes to our energy measurement. We've already indicated what those 3 outcomes would be, but what's the average value? Well, again, we're going to do expectation. This case is a little bit trickier, but it's not hard to do with Mathematica. We're going to integrate psi star, all right? And we're going to, when we integrate psi star with, and we're just going to give it an arbitrary value a, all right? So the result of our integration of psi star operating times the Hamiltonian operating on psi again. So this is what we get. And again, so we're integrating psi star, Hamiltonian operating on our function, and psi. When we do that in the expectation value, we get this result here. There is a 0 in front of it. I am not sure why that is, but that's a result of the Mathematica computation. So this would be the average energy. And you'll notice this has h bar in it, as opposed to our original expressions where we tend to remove the pi and just have h squared. But so this would be the average of our measurements. But again, we've got 3 outcomes, and those 3 outcomes correspond to, going back up to the top, correspond to a situation of, I've gotten past it here, let me go back down, here we go, went too far. So here are the 3 possible results when we do that, and h squared over 8ma squared, h squared over 2 ma squared, and 9h squared over 8ma squared. So we've got those 3 possible outcomes. Outcome 1 has a 25% probability because we're squaring the coefficient. Outcome 2 is also 25%. Outcome 3 is 50%. All right, so we have 50% probability of measuring this, 25% of this, 25% of this. And if we take all those and average them together, we get the result that we have down here. All right. And so we have this situation where we have a possible state which has more than, that is a superposition of several energy eigenfunctions.